So we'll start with the context of our study in terms of who are the different attendees. We'll go about the testability in order to give a clear view on what we are speaking about today. Then we'll go to the collaborative engineering domains, which are of interest today. And we'll see that we go from system engineering to other engineering domains. Then we'll move to the toolings, method and toolings, and the modeling of the different domains. And then we'll go to the an operational use case, we say, targeted and with demos about all the different connection in the different domains. With Spherea first. We are a test solution provider since 1965 for all the phases of life cycle of a product, from virtual testing towards the maintenance test solutions. We are currently involved in different domains such as aerospace, defense, railways, and also energy. So I would say we have a strong experience in different processes, different environments, different constraints, but always focusing on test solutions and test matters. Our partner is ESPCI International, which is an American-based company involved in the major defense programs in the States since 1975, mainly in defense domain. The portfolio of ESPCI is very broad, and today we'll get a view and introduction of Express, which is a tool for all the different aspects we'll speak about today, and but we can have extensions to all the other components of the ESA portfolio. So, in order to just give a large view of what we are speaking about today, we took in account the evolution in system architecture. We all face today, and we've been facing for years, which is in fact that the system architecture complexity is really increasing. We also have very strong time constraints for the different systems. So we have system of systems, we have less time to make the design of the system and also the testing of the system. And those systems are evolving towards years and usage. And so we have some upgrades and changes to master in the different systems. Yet, by doing so, we face more potential failures. Time to restart may increase when failures occurs, and so the availability of those systems, which is, I would like, the key driver for the users, may drop down due to all these different factors. So, if we speak about test, because we wanted to introduce test because we all know you are all specialists of the system engineering, and so let's speak just some few words about testing. When we speak about tests, we have several test domains during the life cycle of a product with different objectives and characteristics. If we speak about all the test is performed during the development of a system, the target is really to validate that the system is meeting the requirements in terms of a verification through the design requirements, the validation through the customer operational requirements, the qualification requirements. Once all these tests have been done and that your system is validated, you go through production. You can produce far more items than only one during the design. But in production, your tests are there to validate that all your products are functional and that they comply with all the validated design. And once you're in maintenance, you may have some different maintenance organization that will use your test solutions in order to validate that your system is, the operational system in the field is functional, and if not, identify what's the faulty elements so that the system can be returned to service very quickly. One interesting characteristic also to take in account is that when we speak about the different test domains, we also face different time scales. This is just, I would say, relative time scales, but we usually speak about months or years for development, hours and days for the production, and years or decades for the maintenance. So if you speak about critical systems, which usually are expensive, it's decades for the test maintenance. So just to summarize, for the design, you want to check for the compliance with your requirements. And today we'll speak about testing, production and maintenance, where your focus is to identify if there is any faulty element, or if your system is functional, and if there is any faulty elements. We could speak about testing the development phase, but in another webinar, and it has already been presented in the Capella community. So today we want to speak about the other part of the test. Oops, sorry. So just quick definitions. What's testability? Because we have some reference definitions for the testability from NATO or French from NORMA. But in few words, testability is a characteristic of a system or an equipment, and the testability is a characteristic about is it possible to detect the failures, and is there any failures? Can we identify the root cause of the failures? This is just a very quick summary of what testability is. So, if you work on critical complex systems, all of you in the community are working in the system engineering area, and of course, with Capella, you can use the Arcadia method and go through the different steps to make the design of your system, and thus going on until functional architecture and a physical architecture. So you will make your system engineering. If you want to deploy your system in the field and it's a critical system, at least you may go to the safety area in order to be allowed to deliver your system. Your customer may request that all the maintenance of your system is already designed, and that the system can be maintained. So there's the maintainability area and also the organization of the maintenance support. And testability is a complementary engineering domain that is focusing on the test, and as we discussed, can we have an assessment of the functional status of a system, and if there is any dysfunctional status, can we get a clear view on what's the faulty elements? So all these systems are complementary. They manipulate different, let's say, concepts, but they all work on the same system. We can say that all the different domains have grown with specific optimized frameworks based on years on practice. We have model-based approaches in the different domains. We all work on the same system, which means that you can have different tools, different methods that all are used on the same system, manipulate some overlapping concepts, and what we'll show today is how we can use Capella in order to make a cross linking with the other domains and get a really collaborative engineering process during the design phase of the product. So what we've been doing is checking the different domains, different modeling in the domains, and not trying to get, I would say, just one tool to master everything, but focus on integration of different tools and segregation on information and identification of where's the reference for this type of information. Because as we all know, whenever you make modeling, you take some assumptions. You may take care if you want to use, or not you may take care, but you should take care. If you're using a model without checking the assumptions made for the modeling. And so we propose or define where should be the references for different concepts. Of course, functions and parts are coming from the system engineering. Failures and effects of the failures are usually mastered by the people working in the safety assessment. The test parts in the testability aspects, and for all the logistic and the support, the product support modeling is the correct areas. So we've been working on some consistency in the meta models in order to be sure that the integration of the different concepts and definitions doesn't introduce any error in the information processing during the design phases of system support, test, and safety assessment. So that's just a very small view on the different workshops done in the modeling analysis for the integration. So now we'll go to the different steps and the integration of the different domains. And for this, I let Benjamin now take the mic.
Today, we would like to share with you a journey to design a critical system with the safety assessment, but also maintainability and testability also in mind. So to do this, we need first to begin with the system design, and for our demo, we choose to create a model of a railway crossing. So the first part was to perform an MBSE approach and to create this railway crossing inside Capella. The next step is to perform a first and a preliminary study on reliability and safety. And to do this, we have developed a viewpoint in Capella called RAMS, and the aim of this viewpoint is to allow system engineer to add specific information about reliability or maintainability inside their usual framework and inside the same formalism as usual. This approach allows to get some feedback from maintenance operators or maintenance shop, and to bring inside the Capella some important information about which elements fail more often than usual, or which measurement could be done to prevent some failure. This viewpoint is used as a connector between the MBSE world and the MBSA world. Our assessment from a customer is that the people who know, who have the best knowledge of the system are, in fact, maintenance operators. And when the system is in operation, when they want to give some feedback to the design office, mainly they will discuss with system architect. So the viewpoint developed allows system engineer to incorporate the different maintenance feedback directly in an MBSE tool such as Capella. Then we'll go through more dedicated tools such as safety assessment or testability tools such as Express to perform more specific studies and generate different algorithms such as the failure procedure tree or some specific monitoring algorithm which could be sent back to the system in operation to prevent some failure or to optimize the maintenance of the system and thus improve the availability of the system. I will show you very quickly the different aspects of the RAMS add-on, but we will show you in live demo with video about the different aspects. First, we defined a failure mode and the stochastic transition between different functional mode to a failure mode. And we also had some characteristic for both failure mode and stochastic transition, such as the failure rate, or for the failure mode, the different information such as root causes, symptom, the next effect, and so on. We also had notion of measurement and hazardous events in order to focus on where we can place a point of measure, which quantity have to be measured, or for the hazardous event, which element, which failure should be one for the team. Then, with these preliminary studies, we can go further with more dedicated tool now to perform safety assessment and then FMECA studies or testability study. And to do this, we use DSI's tools, Express, which first start from a system design where we have a model of our system with some block representing a replaceable unit or a hierarchical architecture and a different interconnection between these blocks. And then from this system design, we can perform one studies where we define different failure mode and failure effect and interaction with the design. We have a FMECA analysis, which is in the MBSE domain. And the second analysis we can perform with the tool is a definition of test and characteristic and performance of test, which allows to perform a testability analysis, which is more in the model-based testing domain. The major outputs given by Express are the reliability of the system, which could be the mean time between failure, but also the intrinsic availability, but also with the different tests defined, the maintainability metrics such as the mean time to repair or the mean time to detect a failure. From the safety modules, we can perform FMEA analysis. We can have FMEA outputs, but also FTA fault tree analysis of the system. one very specific aspect of Express, and which is very interesting, is the diagnostic studies. According to the different tests defined inside the tool, we can create a fault procedure tree, optimized according different criteria, such as the cost of the test, or the time to perform a test, or the number of tests, or the intrusiveness of a test. And then you have a tree like this, which give you a way to perform diagnostic, in fact, yes, thank you, Yann, to show that your system is operational, or you can detect that your system have a failure, and then to isolate the group of faulty components, the suspected components, which host the failure. This output can be used to be implemented inside auto test, or inside the more optimized diagnostic procedure tools given to maintenance operators. Okay, now we will show you some video about all this concept. And first, we will show you the RAM's viewpoint. As you can see, it displays more information inside the physical architecture. And first, I will show you the failure mode and stochastic transition. So first, we define functional mode, and from this functional mode, we can define some failure mode. And for each failure mode, we can characterize it, such as the severity or the failure effect, and also a symptom or the root cause for more maintenance aspect. We also define the transition between functional mode to a failure mode, and from this transition, we can also define which physical component is involved when the failure occurs, but also the failure rate of the transition. Now, we also defined what we call the assertion, which is in fact attached to a failure mode, and then we define the dependencies of outputs with inputs. And also we can then modelize the failure propagation across different output of the function. Then we also defined the notion of measurement, which is a box where we can define some different attributes, such as which instruments are used to perform the measure, but also when perform the measure, but also which physical quantities to measure. And also we specify where to put the measure.
So what's important here is that RAM's viewpoint has been developed in Capella, so that system engineers can interact with people from maintenance and safety, and have in the, let's say, usual framework views I understand on simulation, because as we said at the beginning, models are really specific to different environments, different domain, engineering domains, and we usually face communications issues in between the different specialists, because they used to get what we call viewpoints in Capella.
Then we also define hazardous event to point a very specific failure to take care for further analysis. This hazardous event can be linked to a specific failure mode. From this first studies, we need to go through more dedicated tools such as Express, and to do this, we deal with the what we call the digital thread to perform a seamless integration between the two tools. And to do that, we have developed a tool, a script, which take in input the Capella model and give in output Express items which can be imported inside Express. So now the export is done, and we will now import it inside Express. So we choose the items exported, and now we are importing them inside Express. We have some question about some relevant information, and then when everything is done, we have our model, our Capella model imported inside Express, and now every component and every function defined in the model-based system engineering domain are now directly imported inside a model-based safety or testing tool.
So for the users of Capella, you may right now see that changing a tool, it's the same system we're speaking about, and the modelization is using the same concepts, but display is not so easy to go through when it's not your domain. So now we leave Capella, and we are using now Express to perform safety analysis or testability analysis. And first, what we would like to show you is that Express deals with a system architecture before to deal with a test or safety items. And each block represents a component or a replaceable unit, a repairable unit of your system, but also can represent a black box with a hierarchical architecture behind. What we would like to say also is that all nets representing the interaction between the blocks are also imported, but after the import, they are not displayed, they are stubbed. And for the sake of the demo, I switch them to link between to display link between different components. Each block also have ports which define a flow of source input of data to a sink, and all the tool will use the different propagation flow to perform all the testability and the safety assessment. Now we switch to the first analysis, which is a FMECA analysis. And to do this, we have to define first a failure mode. A failure mode is how a function can be affected by a failure. And then we have to define the failure effect. Failure effect can be defined at the component level. It means what does the failure mode affect the component, and then this failure effect, how this failure effect can affect the next component, in your design, and how this failure mode and this failure effect will affect all your design and so all your system functionalities.
When every failure mode and failure effect are defined, we can go through the FMECA studies, and after setting different options, which mean which relevant information we want to display, the tool compute the different effects and severity of each failure mode defined, and then you have a FMECA computed. You have all very relevant information here. And also, we can switch to fault tree analysis for a specific failure effect. And you have here, in fact, the different faults which can lead to this critical event, and associated the different probability of occurrence of this failure. Now we switch to testability analysis, and to do this, we will define inside the tool a test, and a test is defined first by a test location. In other words, where you can set a measure and a criteria to pass or to fail the test. Also, you have to define the different stimuli which are needed to perform your test, and then the different coverage of different items. In other words, if your test is passed or if your test is failed, which components can be considered to be faulty, or which element could be considered okay. Then, when all different tests are defined, we can now switch to a diagnostic studies, and according to different options, as we said before, such as we don't want intrusiveness, or we prefer to prove that the system is good with a few tests. We can create a fault procedure tree with the different tests defined inside your design, and according to the result of each specific test, we can go further in the tree or switch to a specific branch, and then go to a group of suspect items which can be fault, and then lead to a fault, a system failure. Associated to these studies, we have some metrics such as the probability of detection or the probability of isolation, which characterize the availability,
the performance of the detection. If any failure is occurring in the system, is your system functional or not, which means detection, and if not, what's the faulty element to be replaced? That's the diagnostic.
And then we can use the previous diagnostic studies to import them inside a FMECA analysis. And now, in your FMECA, you have for each failure different information about does this failure is detected, or does this failure is isolated, and in which suspect group you can find the failure. Okay, so now last video. According to this first analysis for both reliability and testability, we would like to improve our design, because for the moment it's not very relevant
So we have a very nice system, which is really functional, coming from the model-based system engineering in Capella. And what we can see here is that it has really poor performances in testability and so maintainability for this system.
So first, we would like to improve the maintainability and thus the availability of the future system. And to do this, we create new tests. In fact, we create new interfaces for specific for maintenance. And after test definition, we will perform the same testability studies done previously. And when we do that, you will see that the global performance of the testability of the system is improved. Okay, generation, and now. So now you can see that the fault localization tree is more complex, and now we have for some specific tests a fault group with one unique component. In other words, you have now the ability to isolate very precisely which components are in fault. And if we go to the statistic, we can see that the different probability are better. Let's do the same thing with the safety for the reliability. And to do that, we can detect in the FMECA study that some elements are too weak in our design. And for this design, we choose to create a redundance. And then when we perform the same FMECA analysis, we can now see that we improve the global availability of the failure rate of our system. So now, in fact, with these two improvements, we have to go back now to Capella to perform a new iteration of our design. And that's we are doing now. And as you can see, I recreate the redundance of the element. And here I create a new maintenance interfaces to detect more failure. And voila.
So what you've seen there is that the people from the testability can work in the framework from referential information coming from the system engineering, and the last topic is for the modeling for product support, and where we can use the relevant information for from the testability, because as we said before, we have different concepts. For example, when you speak about the physical analysis in Capella, you speak about the different components, whereas in I would say maintainability, you need to speak about the spare parts for your system. So for this part, we are using Opus 10, which is a software from Systecon, where you can make a complete modeling of the support organization for your system, where you have all the information coming from the reliability and the maintainability for your system, the cost for the maintenance operations, the capabilities. And with all this information, you can make over a fleet of system a simulation in order to compute what's the cost for getting a certain performance in availability of your fleet. What's interesting, in fact, is to work during the design phase and make regular loops in between the different domains so that you can have a clear view on what's the impact of the evolutions of your system design, taking in account feedbacks from the testability in order to perform more efficient diagnostic and from the support organization. And you can have a clear view on what's the improvement or not you are performing when you change the design of your system. So we are all focused in our system design of to get a functional system, but some key characteristics with a few changes may improve other field of interest. All what we have presented here is consistent with our focus topic from the beginning in terms of system, because the different frameworks such as Capella for system engineering, Express for reliability, safety and testability, or Opus can deal with black boxes, white boxes, and also system sub-equipment. So going from one system to a larger one or hiding complexity because of industrial motors matches with all the different exchanges in between the tools. So just as a conclusion, what we've seen here is that we can have a collaborative model-based engineering in between different domains with different communities working in their own tools, and thanks to the fact that we have access to some model information, we can make some connectors in order to ease the feedbacks in between the different domains, and so that we ensure that while we are designing the system, we are not making a not sustainable system. And also what's important is that thanks to this capability to make quick exchanges, we can really go to an optimization without challenging the time to market, which is, I would say, a key driver for all of us system engineers nowadays. So that's the end of our presentation today. Thank you very much for your attention.
Thank you, Yann and Benjamin. It was great. And we already have a few questions. So let's go in order. The first question by Tony Erwin. Does all the testability analysis occur in DSI Express, or does some of that occur in Capella?
So we really wanted to use the tools for the domain where they are, they have the added value. So as we showed you, we use Capella to allow system engineers to inject or define some basic information, but all the computations is done in the different tools. So computation for testability analysis is performed inside Express.
Okay, that's very clear. Thank you. Another question by Emric. What language did you use for the script converting the Capella model into an Express model? And that's also a question I have, actually.
I think you've seen that it looks like Python.
Yeah, for the moment, it's a Python script.
Yes.
Okay, great. Did you use Python for Capella to read the Capella data, or was it a direct Python reading?
No, not at all. In fact, we find that using Python for Capella was too complex, and we have some difficulties to use it and to parse the model. So we choose to develop our own library to parse the model and then to compute some transformation and then to export it to the Express ML, in fact, the XML document needed by Express.
Okay. Next question by Tony once again. Which tool is used for supportability? If there is a tool, I guess so.
I'm not sure about the understanding of supportability. I would say that for the product support, it's Opus 10, which is a tool from Systecon. And so where we make all the modeling of the support organization of the system that has been designed in Capella and the maintainability or testability performances made in Express.
Okay. I have a few more questions. There's an additional one by Samuel. How is the synchronization and merge across the various models managed? I mean, is the export from Capella to Express incremental? I believe that's the question. And what happens when the Capella model changes and you have to run all that again?
So as we speak about tool integration, we also speak about methods. And so we have traceability in between the objects in Capella and the objects in Express, for example. Yet, I would say for synchronization, say configuration management is the key for the different elements.
Okay. One last question from me. What's actually the status of these features that you have developed? What if somebody would like to try them? Is that something? I mean, do you sell it? How does it happen?
It's not yet decided from us. I would say we are. What you've seen there is the result of a development that has been ended not so late. I would say a few weeks ago. So we are currently performing a test on. We chose some complex models, and we would like to be sure of what are the limitations before providing it, and we've not yet decided how to provide. But we are open to the discussions about on this.
Feel free to contact us.
There is a new question by Tiziano Munaro. FMECA is a purely analytical approach to determine the effect of faults and failures. Do you plan on including numerical simulations as well? For example, to see how certain failures affect system dynamics, such as stability?
So we don't have, I would say, behavioral models in the different or dynamical behavioral models in the different tools. Yes, right now it's purely analytical. What we have started with RAMs is that we wanted to set up, I would say, a feedback from the field in a reliability on the different components. But until now, we've not planned to make, I would say, either dynamic modelings or degradation modeling, because I think that's the question.
Okay, thank you. Do you have any idea on how much time the direct import from Capella to Express is gaining compared to a manual approach where the Express user would have to redefine the component hierarchy and connections and so on? Did you measure that kind of gain?
I can answer.
Yes.
Because I use the Bossa tool. from my experience, we have experimented one approach with two people. The first, I was developing a model inside Capella, and another colleague tried to modelize, not import it, but modelize directly in Express. And the complexity of the model is equivalent to the railway crossing you've seen before. And the gain is around 1 day for this kind of models. You have a few hours to design, but a lot of hours with iteration between the system engineer and the Express user to be sure that each component are equal or identical, and each connection are the same, and the same flow is identical in both ways.
I would say that one major aspect is not only the time you save, but the consistency you ensure. Because as we made the analysis in between the different concepts and so on, we are very confident in the fact that let's say a functional chain, which is what Express is really focusing on, whatever the functions are, but the functional chains, so that with failure propagation is consistent with the design that is used by all the design engineers. So, of course, there is time, but consistency and risk of errors, because as you could see, all the members of Capella communities are, I think, really, let's say, familiar with Capella modeling and reading models. If you go to Express, and I think some of the people may be lost in the different figures, and yet it's the same system. It's not exactly the same objects, because we don't speak about the failures in Capella, but it's the same system, and some concepts are exactly the same, but not displayed the same way. So consistency, I would say, is the real added value.
Yeah. In fact, now when I export my railway crossing model from Capella, I'm sure at 100% that in Express, each component have an equivalent inside Capella. And as Yann said, if I define a functional chain in Capella, we can retrieve it in Express.
Okay, I see. Well, I believe that's a very nice conclusion to today's presentation. So, Yann and Benjamin, thank you very much for your time and work on that.
Thank you.
That was really interesting. I hope everybody enjoyed. So thank you, everybody, for listening. Just a few words of teasing to close this session. The next webinar will be held on May the 19th, 2022, of course, 2022. And it's going to be about getting into MBSE MBSA process with a dedicated tool chain. So quite close to today's concerns. Keep up. This is going to be presented by Jean Godot and Jonathan Dumont by O4Tech. So May the 19th, 2022, stay tuned and feel free to register, of course. I hope you enjoyed this session, and thank you again for your attention. See you later. Bye-bye.